So good afternoon, my name is Kenza and I'm a final year PhD student at the University of Cambridge and the British Antarctic Survey. Today I'd like to talk to you about how we can use Gaussian processes to predict precipitation from large-scale atmospheric features over the upper Indus Basin. So I'll start by introducing precipitation in this area, why it's important, and why it is challenging to predict. So the upper Indus Basin, shaded in green here, is the high altitude part of the Indus Basin, which lies in the Himalayas. The mountains in this area work as a water tower, storing snow and ice in the winter, which is released in the spring and summer. So through this mechanism, the upper Indus Basin supports the livelihoods of over 270 million people by providing fresh water for domestic use, agriculture, industry, and energy through hydropower plants. However, in the face of climate change and increasing water demands, the water security of this area is under threat. And the biggest uncertainty for future hydrological modeling, including extremes such as floods, landslides, and droughts, is precipitation. Despite this, precipitation in the upper Indus Basin is still poorly understood, and this can be explained for three reasons. Firstly, the complex topography makes the distribution of precipitation in this area highly heterogeneous, with large variability over small areas. Secondly, there are relatively few direct measurements of precipitation from weather stations, especially at high altitudes. And thirdly, regional climate models suffer from many limitations in this area. They're both computationally expensive and relatively inaccurate. We can get errors of up to 100% quite regularly, even for seasonal averages. So in this project, we would like to overcome some of these challenges by building a model that meets several science and engineering goals. Using ERA 5 climate reanalysis, we would like to create a model that accurately predicts monthly precipitation over a 15-year horizon. We also want to test whether it is possible to use fields that are better predicted by global climate models. Precipitation is in general one of the hardest variables to predict at a local scale. Well, what if we could learn the mapping between large-scale temperature and pressure fields, for example, and that of local precipitation? If this is successful, we could use such a model to generate future regional predictions from global climate model outputs, which could then rival traditional regional climate models. Finally, we also want to gain some insight into the relationship between precipitation and its drivers. In particular, there's a long-standing interest between understanding the non-stationary relationship between Himalayan precipitation and its elevation. This is also known as orographic precipitation gradients. On the machine learning side, we would like to create a model that can draw representative samples of precipitation trajectories into the future and gauge the probability of extreme events. We also want to encode domain knowledge through a model design, and finally study the trade-off between explicitly including non-stationary behavior in our model. And we're going to do this with a probabilistic machine learning method called Gaussian processes. I know, again. So a Gaussian process, instead of outputting a single scalar value, is going to output a probability distribution for every time and a location. So for every possible value of precipitation, we have an associated probability. Over a large number of points, we can see these as distributions over functions rather than single locations. And we can then draw realistic trajectories of precipitation across time and space, like so. For Gaussian processes, this function space is usually shaped via a covariance function that maps the correlation between each of the points. So let's consider 2 points, x1 and x2. On the right, we can see how the distributions associated with these points, P1 and P2, are correlated to each other using a covariance function K. So here we're plotting the distribution of P1 against P2 on the y-axis. And in this work, we'll be contrasting two classes of covariance function, stationary and non-stationary. So if the covariance function is stationary, then the correlation corresponding the correlation between P1 and P2 is only going to be a function of the distance between x1 and x2. In the case of a non-stationary covariance function, the correlation of P1 and P2 will depend on a more complex function between the values of x1 and x2. and this will give us more flexibility in the types of functions that we can model. That being said, even with a stationary covariance function, we can refine this function space quite significantly using our domain knowledge and by analyzing our data. So let's look at some examples of domain knowledge and data analysis that we'll incorporate into our model design. The first is our knowledge of large-scale atmospheric drivers of precipitation in the upper Indus Basin. The first driver is the Indian summer monsoon, which brings rain from the east in the summer, and it's represented by this orange arrow. And the second are the winter western disturbances, which bring snow from the west, here, which I've represented in this blue arrow. And both of these events follow an annual periodic pattern, which we can build into our model directly. Through data analysis, we also identify 3 new precipitation regimes through soft K-means clustering. These subregions are characterized by different amounts of variance and stochasticity in their precipitation time series, and we'll also use this non-stationarity to design our model. So moving forward to some results, we start by applying a Gaussian process to each of the ERA5 grid boxes in the basin using time, 2 meter dew point temperature, total column water vapor, and the El Nino 3.4 index. To build our covariance function, we're going to do it iteratively by adding climatic variables with the highest predictive potential and seeing where that stagnates. So in this first figure, we show that the RMSE, which is the figure on the left, in millimeters per day, where we have higher precipitation rates with the lighter colors and lower precipitation rates with the darker colors, is basically scaling with the average precipitation rate that you would see with the values. On the second figure, we're looking at the R-squared scores here, so the coefficient of determination. Here in the southeast of the upper Indus Basin, in the red, we have the best performance with an R-squared close to 1. In these cases, the Gaussian process is faithfully representing the precipitation distribution, if sometimes struggling to match some of the monsoon highs. We see that several GPs in the center and the west of the basin are struggling a bit more, and these regions actually correspond to the boundaries between the particular clusters that were shown on the previous slide. So, however, even in these difficult cases, the GP is going to increase the width of its function space to include many possible outcomes, and this can be interpreted as the Gaussian process adjusting its uncertainty for those predictions. So the spatial differences in the R-squared scores suggest that one or more important variables which come into play in the easternmost part of the basin are missing, and these differences could also point to an inappropriate kernel or covariance function design for these locations. Moving forward, we apply a Gaussian process to each of the clusters I presented. We're now going to include location information such as coordinates, elevation, and slope into the model. Here, we plot the predicted precipitation from our models as a function of the ERA5 precipitation for the training and test sets in blue and orange respectively. So the closer the points are to the dashed line, the better the model is performing. And although we're still underestimating the highest precipitation values, this method improves over the single location models. So finally, we can apply the GP to the whole basin this time using a stationary and non-stationary covariance function. In this case, we observe the non-stationary model does a better job at fitting the data during training time. However, it does not generalize well to extrapolating, as shown by the orange points, which are further away from the dashed line. This is surprising, as previous literature has shown that non-stationary covariance functions tend to perform better than stationary ones. However, these cases have mostly been for interpolation tasks or settings. So in summary, comparing all these models together, we can see that the cluster model in blue outperforms both the stationary and non-stationary whole basin models in orange, as well as the single location model in gray. So to conclude, Gaussian processes are a viable method for probabilistic forecasting. Large-scale features can be used to predict local precipitation, and incorporating domain knowledge instead of learning non-stationarity for this particular task and this particular non-stationary covariance function used is better. Looking forward, I would like to conduct more systematic feature selection and model design experiments. I'd also like to compare fitting models to the ERA 5 ensemble data with that of our current results for the high resolution data. And then finally, I would like to retrain using coarsened ERA 5 data and make predictions using global climate model outputs. So that's the end of my talk, and I'm very happy to take questions, comments, and suggestions. Thank you.
Great talk. Great talk, Kenza. Do we have any questions from the room? Okay, I have a question from my own.
Yeah.
So I wanted to know how you can improve your covariance functions depending on this particular set of problems in the Indus Valley.
So how I can improve them?
Yes.
So generally, the way that we do this is by looking at the features that we think are going to be the most predictive, and then incorporating these into the model, testing different, I guess, like operations. You can either do multiplication, addition of these in terms of the kernel function, or you can use a function that uses automatic relevance determination if you think your variables are independent from one another. Yeah.
Thank you.
I think that was a question.
Which one? Yeah.
Hi, thank you. Are you, sorry, my name is Mark Deisenhoff. I'm from UCL and the Alan Turing Institute. Could you elaborate a little bit on whether you already run into the problems of using sparse GPs, so just in terms of like data set size?
Yeah, so at the moment I'm sampling the data points. I'm not using the full data set, but I still managed to get something that is quite decent. Going forward, we could use sparse GPs, but generally these would work better for functions that are oversampled. In this case, does not necessarily guarantee that that happens when we're using the time series, but that's definitely something you need to look into. And then you could also use product of experts or Bayesian committee machine to overcome the sparsity. Sorry, to overcome the scalability. That's what I meant.
Cool. Thank you.
Thank you.
Any more questions? Okay. Shall we move on then?
Yeah.
Yeah. Thank you. Thank you again. So next up we have Mark Gironamata from University of Cambridge.
Thank you. Right. Thanks very much. My name is Mark Gironamata, and today I want to talk to you about some work I've done on trying to downscale in a probabilistic way daily precipitation in ungauged mountain locations and building some spatial coherence. This is work we've done with collaborators, Andrew, Vessel, and Richard, but it also builds upon other work that I've done with other collaborators, also mentioned here. So it's really a joint effort. I'm a PhD student at the University of Cambridge and the British Antarctic Survey. So, I mean, Kenza has done an excellent work motivating like why understanding precipitation in mountain regions is very important. So I'll try and focus on the specifics of my problem. We're looking here into present day precipitation and daily precipitation, which is distributionally and just is a bit different than monthly precipitation in how it behaves, and there's different challenges. Daily precipitation in mountains is subject to very local scale variability and very strong gradients. And the problem of these complexities compounded by the fact that in situ observations, so rain gauges and automatic weather stations are very, very sparse, mostly spatially, but then also you get temporal inconsistencies or temporal sparsity as well. As a result of these, or partially as a result of these, existing gridded products of daily precipitation are challenging to compose and have biases. And that's why we usually resort to physically based modeling. So in this case, for hindcasts, for present day and historical data, we take reanalysis from GCM runs incorporating observations, and then we normally downscale them dynamically using a regional climate model, and that resolves some of the process that happen at the subgrid scale for like GCM resolutions, and help us capture a bit better daily precipitation dynamics. But these regional climate model outputs are still biased in some ways because of the very local scale variability of precipitation. And that's why we usually then resort to a second step of downscaling, which statistical downscaling, in which we choose to correct different aspects of the distribution, right? And in this study, we particularly focus on taking RCM outputs and downscaling them using station data. So data that is spatially and temporally sparse, but it's our best, guess for, an accurate estimate of precipitation in the region. An observation that I want to highlight about, the relationship between these RCM data or RCM hindcasts and the observations is that usually you would expect a reanalysis-driven product like an RCM-driven, on reanalysis and the observations to exhibit synchrony, right? Because in the end, it's observations, matching observations, or pseudo-observations, matching observations. But in this region, because of the lack of data simulation that happens in mountain regions, and specifically, in high mountain Asia, there's only partial synchrony between the daily precipitation, modeled by an RCM and the corresponding observation. So that will motivate our approach. In particular, I argue that it still makes sense to try and make use of this partial synchrony and therefore try and use a regression-based approach. But I think to deal with the partial issue, we then resort to probabilistic regression. And then just another point is that spatial coherence is a good attribute to have, in general, in these types of problems, or to aim towards. So what's our approach? So our object of interest here will be, this probability of y given x and theta, y being daily precipitation and x being a set of predictors that we'll use, to predict daily precipitation, and then theta are the parameters that parameterize these, this mapping. And we're going to make a very important assumption, which is that the probability distribution, factorizes as follows. And what this means is that for each spatiotemporal location n, we're going to assume that the probability of daily precipitation at that location is, conditional on a set of predictors that correspond to that spatiotemporal location, is independent from any other spatiotemporal location. It's a strong assumption to make, but given the sparsity of data, it's a necessary assumption to make, I argue, at least at the beginning. The set of predictors that we use includes, the simulated precipitation, so daily precipitation simulated by the RCM, along with other RCM, outputs, other variables, and also, information such as latitude, longitude, elevation, and day of the year. So more kind of static information that will help us make predictions at any ungauged location for which we have these predictors. And we're going to be mapping it into probability space. So we're interested in this P of y n given xn, and we're going to model this using a mixture model, a Bernoulli gamma mixture model that accounts for both precipitation occurrence, putting some probability mass at precipitation 0, and then also the intensity, basically with this lab component, the gamma component that models different precipitation intensities. And these parameterized by parameters pi, alpha, and beta, sorry. And then how do we do this mapping from inputs to outputs? Well, we've tried different models, but here's an example. I show we can do it with a multi-layer perceptron or fully connected neural network. So this is our initial approach. We've tested these in 3 regions in the Hindu Kush, Himalaya, 3 regions that are span a wide a wide span of the region, and also are very heterogeneous in terms of like different aspects. And then we've conducted a series of different experiments that represent different real world scenarios, such as training in the first row single region models. So models that learn from a single region and then are deployed in each region. In experiment 2, we try and learn a single model that deals with the 3 regions together and therefore leverages data from all regions together. And then in other experiments, we test whether we can downscale in a completely engaged region from learning the model in other regions, or whether we can extrapolate to higher than trained altitudes, which, as Kenta was alluding to, is a big problem in high mountain Asia and other regions. Just to show you some visual results. So in the first 3 panels, what we're seeing is the probability that daily precipitation exceeds a certain threshold, across the region. So the thresholds are 0.1, 10, and 50 millimeters for a given day. That's an arbitrary date. And we see that, the probabilities as the threshold, goes up, the probabilities decrease, which makes sense. But big limitation of this approach is that when we sample from any of these probability maps, we're effectively taking independent samples at each spatiotemporal location, and we therefore get, a kind of a scatter that is not, spatially very coherent in terms of what you would expect to see from daily precipitation, right? So that's one of the limitations of this approach. And because we're in climate informatics and we haven't yet talked about GPs, I'm going to, yet again, we talk about GPs, but don't worry, I won't introduce them because Kenta has done a very good job at it. But in order to induce some spatial correlations and spatial coherence, we're tweaking this approach and adding a latent variable that we model using a GP. So here, the latent variable is f, and now we're predicting, P of y given x and f, where f is modeled by a GP, which is defined across space. And then what it means is that, we can take samples from this GP, which will be, different functions defined across space, and then we can evaluate them at any number of arbitrary locations along this space, in this case, for instance, our stations. And by doing this, we hope to induce some spatial coherence. So, for every, I here being a spatiotemporal location, our probability of daily precipitation will be, is described by this formula here, which is, basically adding the function f evaluated at spatiotemporal location I, and then that's fine. We end up with a sort of like generative model, if you want, because we can sample f's. But to return to the quantity that we were trying to evaluate before, which is P of y given x, we integrate out the latent variable. And we do it this way, but in practical terms, what we do is a Monte Carlo estimate of this integral. And just to point out that what we end up is not anymore like a Bernoulli gamma distribution, but it is a mixture of Bernoulli gamma distributions because of the Monte Carlo estimate, or integrating out that latent variable. So it's a bit more of a complex object. Right. Some preliminary results for this approach. We've tested it in the Swiss Alps and also in the Langtang Valley, which is one of the regions in the Himalayas. We see that compared to the MLP approach, evaluating on held out negative log likelihood, that this approach does better. These are some very preliminary results with using very default GPs, but we've tweaked them a little bit recently, and they exhibit even better performance. So just again to show you a bit visually what I mean here. In the first panel, we have the raw daily precipitation simulated by an RCM, just so that you get an idea of what the input or one of the input looks like. And then on the second panel on the top right, we have the probability of precipitation occurrence predicted by this GP MLP model. So far so good. So even though our model improves upon the MLP, when we sample from this GP MLP probabilities, we still see a scatter, as you see in the third panel there. So it doesn't solve all our problems, but I argue that we've made an improvement, and in some regions you can see a bit more structure. And then the fourth one is just showing you what a sample from this GP, which in this case was using an RBF kernel, looks like. So just to conclude, some remarks. We've seen that we can use probabilistic regression to address this issue of partial synchrony between simulations and observations. We've also seen that downscaling daily precipitation in engaged locations is feasible, and we've looked at different real-world scenarios. Also, adding a latent variable seems to help improve the spatial coherence, although it doesn't solve all of our problems. And we're currently investigating transfer learning efforts from, say, the Swiss Alps, the Rockies, and data-richer regions to these, data scarcer regions such as the Himalayas. So with this, I conclude, and thank you. Any questions?
Thank you, Mark. Should we take some questions from the room? Okay, go ahead.
Thanks. One difference between the Alps and the Himalaya region is that Himalaya, the elevation is really high, and then we don't have much observations above 5,000 meters above sea levels. Most of the stations in there, it's almost like below 5,000 meters. So do you think the model you are trying to do here can really capture in those like high elevation regions in the Himalayas? It's above 5,000 meters where there's no observation exists.
Yes, so I think we've conducted some experiments to see whether it generalizes well to higher than trained stations, but obviously in order to test that you still need some stations that are high altitude. So and the highest altitude stations that we have, yes, are around just below 5,000 meters, some slightly just above 5,000 meters, but there's not many stations. And so I think we can only say that it generalizes well up to the point where we've tested. Above that, I think it's just very difficult. So I don't know really. But what we've seen is that we can train on a bulk of stations around 3,000 meters and then evaluate on the 3,000 to 4,000 meters, and it does improve results.
Thanks.
Thank you. Should we take one from Slido? So it asks do you think the model can be useful in high elevation areas that are never been observed?
That's the same question.
Oh my God, I'm so sorry. So I would like to ask another one. So you talk about RCMs and the biases that they have. Could you explain those more for someone who does not know about them?
Yeah, so specifically with the type of RCMs that I was using, in which they are driven by reanalysis products. Reanalysis products should, in theory, capture well the large scale features of the atmosphere, and then using RCMs to downscale them should get you a better representation of some of the more local processes. But specifically, say for high mountain Asia, there's these RCMs which might be run at 5, 6, 3, 4 kilometer grid cells, still do not have the resolution to capture all the local scale processes that happen at the very, very local scale. And then that's where all these parameterizations happen. And sometimes, as a result of these, you get some biases.
Right. And also about the transfer learning that you're talking about from the Swiss Alps, what is the feasibility of those that you're looking into?
Well, I guess just conceptually, I'm thinking is that the main mechanism of precipitation in mountains, or a very important one, is orographic precipitation. And what I'm claiming is that mechanism conditional on enough information about your context, so all the large-scale atmospheric features, the topography, everything, the mechanism is the same, and climate models simulate it using the same equations. So provided that there's enough information, I think there might be something interesting to learn from these regions, and then that can be transferred into into the data scarcer regions.
Great, thank you. Any final questions? No? Okay, thank you. Next we have Lenia Manco from CMCC.
Sorry. Where is the mic?
Hello everyone, it's a pleasure for me to be here. I am Ilenia Manco and I am PhD student at University of Bologna. This work is in affiliation with the CMCC Center Foundation in Italy, and we'll explore the capability of the GAN, the power of the GAN for statistical downscaling. We are aware that there are two types of downscaling, statistical downscaling and dynamical downscaling. About the dynamical downscaling, it resolves the complex relationship between physical variables by solving the partial differential equation. And this is the advantage of the dynamical downscaling. But it is extremely time-consuming and expensive. For this reason, the large part of the scientists moved through statistical downscaling, because statistical downscaling, it is very computational efficient and flexible. But it establishes an empirical link between a set of predictors and a set of predictants. What is the big difference between this study with the other study? We have two different big differences. The first one is that in this study, we consider the GAN, the Generative Adversarial Neural Network. The GAN usually is using for imaging, not for climate application, but it is very powerful for this application because it permits to generate, starting from low resolution, dataset at high resolution. But another big difference is that we consider not only high-resolution real dataset for the training period, but also low-resolution real dataset. In this way, this upgrade maintains the spatial coherence between the fields at different resolution in input. For the high resolution, particularly, we use VHR real dataset. VHR is a dynamical downscaling product from ERA 5 at 2 kilometers of horizontal resolution by Cosmos CLM over the Italian peninsula and part of Europe and part of Africa. For low resolution, we consider ERA 5 reanalysis at 31 kilometers of horizontal resolution. And our purpose is to have a downscaling from low resolution at 31 kilometers to low resolution at 2 kilometers of horizontal resolution, directly with GAN. Okay, but we have many types of GAN, because the GAN is a class of methods. For this study, we choose to use super resolution approach, because the GAN in super resolution approach has the capability to produce new dataset at high resolution. In general, the GAN is composed by two different components, a generator and a discriminator, that plays a min-max rule. The generator has, the purpose of the generator is to produce new artificial dataset, and the purpose of discriminator is to learn to distinguish real and artificial dataset. In general, I report a general scheme of the GAN in the figure, but the bigger difference is that we used real randomic input sequence, but we use real dataset also for low resolution. But I divided this presentation in three big points: input data preprocessing, architecture definition, and the analysis of the results. About the input data preprocessing, we follow three different steps: domain definition, split of the dataset, and normalization. About the domain definition, during the domain definition, we cut the domain of the interest from global data. In our case, this is the domain that we take into account, but we tested this algorithm, this new algorithm, with different domain, a different dataset. But today, I show you the results for this specific domain. About the split of dataset, this is a common practice in machine learning algorithms, and we choose for training 10 years with daily frequency, and for tests 5 years with daily frequencies. The most important step is the normalization in preprocessing. Why? Because the normalization has an impact on the results of the GAN, and for this specific architecture, we choose to normalize the input between -1 and 1. Why? Because the last layer of the generator that we developed is a hyperbolic tangent, but we tested different type of normalization and selected the best one. After, architecture definition. This is the core of our research. Why? Because this is a new GAN, a new architecture for this specific purpose, statistical downscaling. In general, we can describe our architecture with this scheme. In the first step, we have a training. During the training, the GAN taking input high-resolution real dataset and also low-resolution real dataset, and give you in output high-resolution training dataset, generator and discriminator errors, and the best important about the training, the best generator. Why? Because we apply the best generator to low-resolution dataset during the test period, and we have in output a high-resolution test dataset. We have, during the test period, only low-resolution dataset, and our purpose is to obtain for the same period the high-resolution artificial dataset. After, we choose to compare this result with the dynamical downscaling. In particular, this is the architecture of the generator and discriminator we developed. The generator is composed by 4 linear layers, and the linear activation function, and in the last layer we have an hyperbolic tangent that gives in output values between -1 and 1, and then we denormalize with the empirical function this output. And the discriminator is composed by 4 linear layers, leaky value activation function, and G-put function. In the last layer, we have a sigmoid function. The sigmoid gives you in output the probability that the image generated by generator is real or is fake, comparing the results with the dynamical downscaling during the training period. In the table, you have some details about batch size, number of epochs, learning rate, and the loss function. In particular, we use 2 different types of loss function: adversarial criterion with binary cross entropy, and pixel criterion with mixed error. Okay, this is in general the architecture. Now we go to the results. We analyzed the different field, but the first one is the daily temperature and meter. This activity is done. The other one are ongoing. About the results, the first step is to evaluate the power of the reconstruction of the GAN. So at right, you can able to identify at left VHR real dataset for 1 random day during the test period, and at right ERA 5. We starting from ERA 5, and we would like to obtain the details of VHR. After 100 epochs, we obtain with GAN this result. We have the same patterns and very, very similar values, but it is only qualitative check. But if you have more quantitative results, we analyzed also error metrics such as root mean square error, MAE, and bias, and so on, and the correlation. And we're able to say that the bias, the error metrics in general, are low with some peaks along the alpines and apennines along the complex orography, but are low, and correlation, the Pearson correlation is very high. But we analyzed also temporal and spatial correlation. When you talk about temporal correlation, the GAN hasn't the time dimension. But this is only the measurement to accordance between the high-resolution dataset and the low-resolution dataset. About the GAN is in green and the VHR is in blue. The curves are overlapped. Instead, era 5 has a shift respect to the high-resolution dataset. The correlation is reported in time plot, and at left we have an indicator of an index of spatial coherence, spatial correlation between VHR real dataset for test period and GAN, and the points are distributed along red line. This is a good indicator for the GAN. If you have a more complex results, we can look at probability density function for the distribution and extreme values. And in this way, we complete the sum analysis for this variable. And about the probability density function, is evident how we, starting from a green line, that is era 5, we able to reproduce the blue line, that is VHR, and the peaks are the same, and the curves are overlapped in many points. And at the left, we have an indicator of extreme values because we analyzed for each data set the percentile, and we consider one box plot for each data set. In general, GAN replicates the median and whisker extension of the VHR data set instead for each percentile. Instead, low-resolution dataset shows lower temperatures and wider dispersion compared to high-resolution dataset. About daily total precipitation and wind speed, the activity are ongoing, and we are evaluating the input normalization, different input normalization, different batch size and weighting associated with the loss function. Also, the possibility to use different input data frequencies. Why? Because normalization, loss function, batch size, and so on have an important impact in total precipitation and with speed in particular on the model convergence, speed of convergence, and the model's ability to learn relevant pattern. In conclusion, the developed GAN demonstrate the ability to replicate patterns and median values. We are able to reproduce distribution of the high-resolution real dataset, and also is able to capture extreme values. About the computational details, we spend for the training for 10 years with daily frequency 8 hours, and for a test period for 5 years, 2.5 minutes. About the next step, I would like to replace the linear layers with convolutional layers for total precipitation and wind speed, because for temperature it's okay, linear layers, but for total precipitation and complex in general field are better using convolutional layers, and evaluate the impact of using a different loss function and porting the model on GPU to improve computational performance. Here I report some bibliography, and thank you so much for your attention.
Thank you. Thank you, Elena. We have one question in the room.
Hi, Elena. Very good. So I was wondering, at one point you were showing the box plots.
Yeah.
And they were like the gray box plots.
Box plot here. No, sorry, but I think that not present. I don't know.
Yeah.
Ah, okay.
So I see that in the middle, near the middle of the distribution, the gray box plot, which I cannot, my hindsight doesn't help.
Yeah.
I cannot see what is the gray box plot. I see there is a lot of deviation from the other two.
Yeah, thank you for the question. Okay, yes, in general, the gun replicates median values and whiskers, but we have a slight shift in the gun upper and lower whiskers respect to VHR. About the box plot, in blue, we have VHR, in white, we have gun, and in green, we have ERA 5, and ERA 5 is a lower resolution dataset, and is evident how gun is able to reproduce extreme values respect to ERA 5 at a low resolution dataset. And this is also an indicator of the extreme values, because before we investigate spatial coherence and temporal coherence, but usually artificial intelligence algorithms are not very able to produce good results in terms of meteorological or climatological results about the extreme values. For this reason, we investigate each percentile.
Really nice. In fact, I can see that you are doing much better.
Yes.
And a similar question, if I can. In the same, is another plot that you were showing I think the climatology, this one, the one on the top left.
Okay.
You have the ERA 5 is the red one.
Yes, okay. ERA 5 is the red, yes. Blue, we have VHR, and in green, we have
the
gun.
Do you have any idea why ERA 5 is lower?
Okay, yes, probably it depends by the normalization of the input. In fact, I tried different type of normalization and I have different results, but the shift is evident in all normalization, because the ERA 5 at 31 kilometers not reproduce the same patterns that are reproduced by VHR, higher dataset in general. So this shift is evident for all normalization, but is more evident for this specific normalization that consider high resolution is normalized respect to high resolution for training period. And low resolution is normalized by respect to low resolution in the same period. And during the test period, I normalize low resolution respect low resolution, and denormalize the output respect VHR during the training period. This is the best procedure to normalization because it's more coherent, physical coherent. But the shift is evident in all normalization.
Thank you very much.
Thank you.
Thank you.
Thank you, Elenia. Great talk. In the interest of time, we're going to move on to our next speaker, Daria.
Thank you. Thank you.
Daria Botvinko.
Just check if they... Okay, spoiler. It's okay, it's not sure. Okay. Hello, everyone. I'm Daria Botvinko, PhD student at IMT Atlantique and the National Engineering School of Brest in France. And my work is focused on the simulation of Lagrangian trajectories at the sea surface with deep learning methods. So first of all, why are we interested in simulating trajectories at the ocean? Following trajectories in the ocean is important for environmental issues such as plastic drift, oil spills, or marine species migrations following. It's also important for search and rescue missions. And finally, Lagrangian studies can allow to deeply studying the ocean general circulation models. So usually when we simulate Lagrangian trajectories on the ocean surface, we refer to the advection equation, which is a simple integration of the velocity of the ocean currents at a given position at a given time. However, this representation of trajectory is sequential and pointwise, which leads to the propagation and accumulation of errors through time. Those velocities usually come from the ocean circulation models. In this presentation, I will mostly refer to the reanalysis model, which is the combination of numerical ocean simulations combined with observations and then reanalyzed in the past in order to be as close as possible to the observations. The models that I will use for this study are often have the resolution, spatial resolution of approximately 10 kilometers and a temporal resolution of 1 day. You can already have an intuition that all the dynamical processes that are happening under the 10 kilometers and 1 day resolutions are not taken into account in such models. As a consequence, these advection representation of Lagrangian trajectory are mostly limited to the first computational capacities necessary to resolve those underlying complex physical processes, but also limited to the uncertainties due to the spatiotemporal resolution of the circulation models. And finally, they are limited to the pointwise advection representation of a trajectory. What I want to do here is to propose a deep learning tool that would be able to simulate a Lagrangian drift. Then I will compare my model to the existing numerical advection tools. And finally, I will explore how different geophysical variables can improve the simulation of Lagrangian trajectories. So the model that I propose is called DriftNet. DriftNet is the is inspired by the Eulerian representation of Lagrangian drift, described by Fokker-Planck equation. If you're not familiar with this equation, intuitively you can consider it as, instead of simulating a particle in the ocean as a sequence of latitude and longitude in time, you simulate a particle as a propagation of its PDF in time. And by PDF, I mean probability density function. And in this case, it's a probability of a given particle in the ocean to be in this or that position in the ocean. So basically, my DriftNet is composed of 2 blocks. The first block is learned operator epsilon, which has to encode the initial position of a particle in the ocean, called here y0, which is a 2D representation of my particle's position, combined to the underlying velocity field from the ocean circulation model. Once I encoded both, I expect my DriftNet to propagate the initial PDF y0 in time and to produce the sequence of 2D PDF in time, which is called here y. Once I get this y, I put it into a block, which is called here m, in order to map the 2D PDF into a sequence of latitude and longitude positions. I will take a second for you to assimilate a little bit all that, because it's not that easy. A small visualization may help you. So on your left is the input to my DriftNet. It can be any geophysical field, but for this example, I take the U and V components of ocean currents combined to the y0, which is the initial PDF of a particle in the ocean, okay? Then everything is passed to the operator epsilon, which is composed of a 2D convolutional block, followed by a conv-LSTM block, followed by a final 2D convolutional block. And then I expect my DriftNet to retrieve a spatial-temporal latent encoding of my trajectory, which I then pass to the operator m. And this operator gives me the usual representation of the trajectory, which is just a sequence of latitude and longitude in time. I expect the DriftNet to capture relevant information at non-local-wise space-time scales, in the contrast to the usual pointwise advection scheme. Now I will go to the experimental design. So to validate the method and to test it in different cases, I propose to study first 2 different regions that are characterized by very different dynamics, which is Northeast Pacific and Gulf Stream. Then I use a numerical advection tool, which is called ocean parcels. And I propose to conduct 2 benchmarks. The first benchmark, called B1, is a virtual case study, and the second benchmark, B2, is a real case study. In this presentation, I will only focus on Northeast Pacific to simplify the explanations. So the case study regions, as I already said, I will only focus on 2 boxes, black and green, in the Pacific region. So for the benchmarks, both benchmark are using ocean parcels in order to generate virtual trajectories using ocean parcels numerical advection tool. For the first benchmark, I will refer to 2 models. The first circulation model, called here Nature Run, is a simple free run model. No assimilation, no reanalysis, just a numerical ocean model, okay? The second model that I call here OSSC, it's a virtually assimilated free run model. They are both having the same spatial and temporal resolution. And just to give you an intuition, the first model, Nature Run, you can consider it as a case where, imagine that we were able to observe the ocean at every location all around the globe, then this state would be called Nature Run, okay? So Nature Run is a fully known ocean state. And the OSSC, I call it degraded model or partially observed model, which is equivalent to the real use case of reanalysis or assimilated models, okay? For both models, I generate trajectories. The first data set of trajectories, called here L1, is the ground truth for my study, and the second data set of trajectories, L2, is considered here as a baseline. And my goal here is to train a drift net on the degraded model, which in the real use case would be a reanalysis model, to reproduce trajectories from the Nature Run model. Okay, perfect. Let's move on. We'll not focus on this. In the real use case, so in the second benchmark, I actually do have the real trajectories that come from Global Drifter program. This program is a data set of floating buoys deployed all around the ocean with an anchor deployed at 15 meters depth. And they are measuring the velocities of the currents and sending their position to the satellite every 6 hours. So in the real use case, this is my ground truth. Just to give you an intuition about the deployment location of drifters all around the globe. As you can see, we have a lot of them. And finally, the baseline for the real use case would be, again, the ocean parcel simulation, or in other words, the virtual particles advected from the operational assimilated reanalysis GLORIS 12 model, which has the exactly same spatial and temporal resolution as in the virtual case. Okay? So basically, we have a fully controlled virtual framework and a real use case. And the first benchmark will allow us to validate the method and then to test in the real use case. Okay, the last function that I use for this study is a weighted sum of the MSE between the ground truth and simulation and the Léo index. And I compare my method to the numerical advection tool ocean parcels and a simple LSTM and a simple CNN models. So the results for the virtual framework are here. First of all, what I'm trying to see is whether my drift net is able to reproduce trajectories if I give to it the fully observed ocean. So if I was able to fully observe the ocean, the drift net would be almost perfectly able to reproduce trajectories with 5 kilometers mean separation distance at the end of 9 days of trajectory. So it's very small error. The Léo index of 0.06 and the mean absolute error between the decorrelation time, which is called here Lagrangian time scale, is of 0.14. And my method is outperforming the other state-of-the-art models. Just to give you an intuition about the error of the baseline ocean parcels method. So we significantly outperform the baseline too. But in the real use case, we actually we do not have access to the fully observed ocean, right? So what we want to do is to see if I give to my model the degraded ocean circulation model, the OSSC, what I want to know is whether DriftNet would still be able to accurately reproduce trajectories. And here what I can see, so the first row is a numerical advection tool. The second row is the proposed network. And as you can see here, the DriftNet is outperforming the baselines, especially the baseline ocean parcels, by more than 15% in terms of mean separation distance at the end of 9th day of trajectory. And it is outperforming the baseline by more than 18% in terms of Leo index. The discrepancies in Lagrangian timescale, I don't have time to explain it right now because I see that I only have 1 minute left, 2 minutes left, okay, but don't hesitate to ask me after. Just to give you an intuition about what the trajectory look like. So the L1 is the ground truth, the L2 is the ocean parcels baseline, and the blue line is a proposed method, DriftNet. So as you can see, in the most cases, DriftNet is consistently outperforming the baseline. Let's move on. Now what I want to do is to test what other geophysical variables can improve actually the simulation of my trajectories. What you can see here is that the first row is always the same, it's the baseline. Then the DriftNet fed with only velocities from the degraded model, as you previously seen. But then what is interesting is that I'm trying to give to my DriftNet the fully observed SSH field. And here you can directly see the improvement by more than 40% in terms of mean separation distance, meaning that if we were able to perfectly observe the ocean with satellites, we would be able to reduce the error in Lagrangian drift simulation by more than 40%. What is also interesting is that the combination of the velocities from the degraded model with the fully observed SSH reduces this error even more by more than 56%. And finally, I also tested the case where I combined the velocities from the degraded model and the fully observed SSH and SST. And this combination reduces the error even more, which is incredible. However, in real life, we obviously do not have access to the fully observed SSH and SST. That's why, just to conclude and give you a little feeling, I tested the same thing in the real use case, okay, with real drifters, with real SSH, with real SST, and with velocities from GLORIS 12 reanalysis model. And you can see that the results are in line with the results from the virtual framework. We have a slightly smaller gains, obviously, because the SSH is not observed everywhere on Earth. And the same for SST. And I also tested winds from the reanalysis model, the ERA5, which gives me the best results in terms of mean separation distance, but we still have some discrepancies in the Lagrangian timescale. But the conclusion here is that the combination of the velocities from the reanalysis model with the observed variables such as SSH gives the best Lagrangian simulation. Okay, I will conclude here. So DriftNet is able to reproduce advection. Yeah, we've seen it in the first validation of the concept slide. DriftNet is able to simulate trajectory given ocean reanalysis data, perfect. DriftNet is also able to simulate trajectories given different geophysical fields, such as SSH, SST, but also winds, waves, ocean color. DriftNet is a differentiable model, which means that it allows to inverse the input geophysical fields, and it allows also to investigate which are the biases in the underlying circulation model, for example, that we could correct with deep learning. And finally, DriftNet is able to generate trajectories across various geographical regions. Thank you.
Thank you. Thank you, Daria. We're just going to end this session in the interest of time, but everyone can let her know whatever questions they have. Okay, thank you. Thank you.
Hello everyone. So I think we have Amin online, I believe. Let's advance the slides.
There we go.
Thank you, Andrew.
I've got the intro. Cool. Yeah, thank you. Maybe we can give one more round of applause to all of our lightning talk speakers. Some really great presentations.